This is the fourth tutorial of Classification Using Machine Learning and Introduction to Classifier series. In this tutorial, we will discuss the support vector machine classifier and how to program it MATLAB by using the PR tools. Okay, let's start the tutorial. Support vector machine is a supervised learning method that looks at data and sort into one of the two categories. Support vector machine, in short SVM, is useful for binary classification for the data having exactly two classes. It classifies data by finding the best hyperplane that separates all data points of one class from those of the other class. The best hyperplane for an SVM can be defined as the most suitable virtual partition between the two classes in multidimensional space. To understand its working, let's take an example to classify two types of fish. We took the labeled data of two types of fish, salmon and mackerel. The SVM creates a partition that can segregate this data into two groups, such that whenever a new query is fed to the model, it can classify them correctly. In the next slide, you will learn how the SVM work. Suppose you are provided with a labeled dataset containing length and weight of two types of fish, salmon and mackerel. Look at the table in the slide. Now, let's plot this data. Weight on the x-axis and length on the y-axis. Afterward, we draw a hyperplane to segregate salmon from mackerel. This line can be drawn in several ways. However, to predict the type of new data, we should split the data in the best possible way. We can see two groups separated by the green line. On the left side we have mackerels, and on the right-hand side, we have salmons. Here, it can be seen the green line has the maximum space that separates the two classes. In technical terms, we can say that the distance between the support vector and the hyperplane should be as far as possible. Support vectors are simply the coordinates of individual observation. Here, S+ is the shortest distance to the closest salmon. S- is the shortest distance to the closest mackerel. The addition of S+ and S- is called the hyperplane margin. Then, by finding the maximum hyperplane separation to both classes, we can get the optimal hyperplane. Once the optimal hyperplane is determined, the model confines which side the new data fits. If we select a hyperplane having a low distance margin, then there are high chances of miscalculation. In this example, a linear kernel can be used. In the next slide you will learn more on SVM kernels. Now, you will see the benefits of data transformation to determine a suitable hyperplane. If you have a data which looks like figure A, then linear SVM will work fine. But, what will happen if you have data as shown in figure B, where one set of data lies in the middle of the other one? Will linear SVM work here? The answer is no. So, it's necessary to move away from 1D view of data to a 2D data view. For this transformation, we use a kernel function y equals square of x. Now, look at figure D. You are given with a 2D dataset, where squares are surrounded by circles. Here, to determine the best hyperplane, you need to transform your data from 2D space to 3 space, as shown in figure E. This can be easily tackled by using different SVM kernels. That allows you to operate in the original feature space without computing the coordinates of the data in a higher dimensional space. Some of the examples of SVM kernels are linear, nonlinear, polynomial, radial basis functions. Some of the advantages of SVM are: SVM automatically addresses the high-dimensional input space or the curse of the dimensionality. They can be used to avoid the difficulties of using linear functions in the high-dimensional feature space. And the optimization problem can be transformed into multidimensional space using appropriate kernel. Works well with even unstructured and semi-structured data like text, images, trees or sparse document vectors. It can handle millions of tokens. SVM naturally avoids bias and overfitting problems by using regularization parameter and shown high accuracy. SVMs are essentially binary classifiers, however, they can be adopted to handle the multiple classification tasks. The two approaches commonly used are the one against one and one against all techniques. Therefore, SVMs are well suited for classification of images, and face recognition. They can also be used for binary classification such as spam filtering. And in medical domain for classification of genes, diagnosing diseases like cancer diagnosis and other biological problems. Finally, this slide provides MATLAB's PR tool method for SVM. You can refer to the link provided in the video. To program a classification model using SVM classifier. The arguments provided to the SVM method are: A is the dataset for training the model. Then, you need to define the kernel type. C is the regularization parameter. This method returns the mapping function and the object indices of support objects. I hope this tutorial improves your understanding of the state vector machine classifier. If you have any question, please comment. Thank you for watching the video. Please subscribe to my channel and like the video.